Let's take a look at an example now. And the first example I want to look at will deal with comparing two population variances. I want to take a look at the variability between two different groups and see if there's a difference amongst them. Now, first of all, the data type is going to be interval or ratio. That should have been obvious to you as soon as I said I'm going to look at the variances. Variances don't have any meaning for nominal or ordinal data. Distances have to have meaning before variability has meaning in terms of the variance. So, the data types applicable here will be interval and ratio data. Now, having reliable information regarding the mean or the median can be extremely important. And it very often is incredibly important. But also having that additional information regarding the variances, how the data is spread out, can often be even more important depending on the process you're looking at. Now, a very common example would be, take a look at Pepsi Corporation. They're bottling, say, 12-ounce bottles of soda. And for them, not only do they need the mean, the average, to be 12 ounces or incredibly close to it. I mean, they can't go out with an average of 11 ounces and advertising 12 ounces. They end up with a class action suit. So they have to have 12 ounces or incredibly close to it. That's just the start of it. If the variability is very large, then what that's saying is they're wasting a lot of product because bottles are overflowing. And a lot of bottles will be coming off the assembly line or the production line empty or half full. That can create a huge problem. How often have you gone out and bought a six-pack of soda or some type of beverage and the can or bottle has been half full or empty? It happens, but it's very, very, very rare. I think in my lifetime, I've only seen like 4 or 5 of them, and maybe 3 of them students have brought to me and shown me after I've discussed it in class. So yes, it does happen, but it's extremely rare. That's because they do a good job controlling the variability. They want the variability to be very narrow. In addition, by nailing that variability in terms of the wasted product, that could turn into a savings of hundreds of thousands or $1 million a year just by making sure we're not losing product because of overflowing. So the idea of controlling variability is extremely important, particularly in a production type setting. Let's take an example here. This particular example deals with a furniture manufacturer. And what they're concerned about is the number of blemishes on furniture coming out of the factory. So they did a test run where the number of blemishes on a specific piece of furniture is recorded for 15 consecutive work shifts, both from the currently used assembly process and this new process that they're trying to test, or they're comparing. Now the question is there evidence to suggest a new process reduces both the typical number of blemishes? Obviously they want to decrease the blemishes at all possible. The typical number, we're talking about the average, possibly the median, and the variability. So they're interested in both the variability and the typical number of blemishes. Typical meaning another word for average. So if you haven't already, I would pause the presentation if I were you and take a look at this data and enter the data in your calculators because this is what I'm going to be working with. Now, I am personally, in my calculator, if you want to follow along with me exactly, the current technique I entered in L1 and the new technique I entered in L2. So if you want to follow me keystroke by keystroke, that's where you may want to put your data. Okay, at this point, I'm assuming that you have the data entered. And before I address the idea of the means, I want to first address the variances. And the test that we'll be using is going to be based on what's known as the F distribution. Now, so far we've looked at the binomial distribution. I believe that was the first named distribution that we worked with. We took a look at the normal distribution. We've worked with the T distribution. Now we're working with the F distribution. The F distribution we work with specifically or use specifically to address variability. Now, the F distribution is always non-negative, meaning the test statistic is always either 0 or positive. It's impossible to have a negative value. And I'll show you why mathematically in just a moment when I show what the actual test statistic consists of. The distribution is not symmetric. It's actually skewed right. And just like the t-distribution, remember when we looked at the t-distribution based on the degrees of freedom, and the degrees of freedom was n minus 1? That actually dictated the shape. It was always mound-shaped, but for small degrees of freedom, meaning small sample sizes, the tails were heavier. If the normal curve was down here, the t-distribution was up here on the tails. So as the degrees of freedom increased, meaning the sample size increased, the t-distribution, although it stayed mound-shaped, converged to or became essentially a standard normal. Well, that's the same with the f-distribution. It does not become a standard normal, but the f-distribution is actually a family of distributions where each member of the family is actually defined by its degrees of freedom. And the degrees of freedom for the f distribution is slightly different than for the t. Yes, it is n minus 1, but for the t distribution, we looked at the degrees of freedom because, or in terms of n minus 1, because there's only one n. There's only one sample. But here, the f distribution is based on 2 samples. So I'm going to have the degrees of freedom in the numerator, I'm going to say n1 minus 1. And degrees of freedom in the denominator, n2 minus 1. So there's 2 different degrees of freedom. We do not have to have the same sample sizes. So based on both sets of degrees of freedom, that will actually determine the shape of the f distribution. Okay, the assumptions, just like every other test, there are certain assumptions that we must satisfy or reasonably show are satisfied to properly use this technique. These are going to sound very familiar to you. At least the second one will. The sample data was obtained from 2 independent populations. Well, we discussed the idea of independent versus dependent earlier. When we go back to this situation with the furniture blemishes, we have 2 separate assembly processes. They're clearly independent. There's no connection between them. Now, this is the part that's going to sound familiar to you. The distributions of both populations are normal. Well, when we did a t-test, we had to make sure the population was normal. So we either applied the central limit theorem or we took a look at a normal plot. Well, here we have 2 samples. So we're going to do the exact same thing, only with both samples. Both have to be normal. If one of them is not normal, all bets are off. The f distribution is not where you want to go. And actually in this course, unless your professor brings in some other techniques, in this course we typically won't even address the idea of comparing variabilities if the data is not normal. Either central limit theorem needs to apply or the actual data itself has to suggest the populations are individually normal. Okay, so on the data that we have, let's switch to the calculator here quickly. Okay, let's switch to our calculators, and the first thing I want to do is take a look at normal distributions. So I'm going to go to norm plot, run the program, start in a list. L1 was my current technique. There's my normal plot. So if we go back to the screen here briefly, I'm going to draw my normal plot. And just like before, I'm not going to worry about making it too terribly artistic for my students. I just want to be able to look at what I drew and then look at the calculator and say, yeah, they actually did it. So this is the current technique. And then, of course, I need to do it for the new technique. So let's switch back to the calculator. Clear that one. And by the way, in case you haven't figured out yet, the way the screen is right now, I just finished running the norm plot program. If I simply hit enter, it's going to run it again. It's going to do that last command again. So the stored in list, my data is in L2. And I'm looking at that thing, yeah, that looks pretty good. So switch back to the screen here and just very quickly look at or draw roughly what it looks like. That's close enough. So both of these look okay. These are reasonably normal. If the samples are reasonably normal, both samples are reasonably normal, the implication there is that the populations must be also reasonably normal. So, all right, I already addressed the idea of them being independent, no problem. The normality looks like no problem. So let's go ahead and actually set up our hypothesis test. Now, the hypothesis test based on the F statistic is going to be based on the ratio of the variances. So I have my sigma squared, the variance of the sub O for the old, which I believe on, let's switch back here. I called it current. This is make it old so it matches. This is what I'm talking about here. All right, for the old, divided by sigma squared, the new equals 1. Well, think about this for a second. If I take two numbers that are the same and I divide them, I look at the ratio. Well, that's going to be 1, right? 3.75 divided by 3.75 is 1. And that's what this hypothesis test is doing. It's comparing the ratio. And the reason it's comparing the ratios is because the actual F-test statistic, based on the degrees of freedom, remember I said there's numerator and denominator degrees of freedom? Really, what this amounts to is, I'm going to call it S1 squared divided by S2 squared. That's really what the test statistic actually amounts to. Hence, numerator degrees of freedom, denominator degrees of freedom. Okay, so in this case, I want to take a look and see if my new technique has greater or less than variability than my old technique. Now, the way this is set up is if the new technique has less variability, that means the old variance is bigger. So the numerator is going to be bigger than the denominator. Well, if the numerator is bigger than the denominator, then the ratio is going to be greater than 1. And that's what this is suggesting here. This is actually equivalent to saying, and you could write it, I'm going to scribble it down here, sigma squared old is greater than sigma squared new. These are saying the equivalence. The only reason I write them like this is because they agree with the way the test statistic actually is written or is actually calculated. This, again, you could approach like this. Sigma squared old equals sigma squared new. Because with a little algebra, divide both sides by sigma squared new, and this is exactly what I get. So it's two representations of the same thing. Okay, so I have my assumption satisfied. I have my null and alternative hypothesis set up. My alpha, I'm going to stay with 0.5. So now let's just go ahead and actually do the test. The test itself, go to stat, test, and two-sample F-test. So let's switch to the calculator and take a look at that. So we'll clear that normal plot, get rid of that. See stat, go to test. The two-sample F-test is actually toward the bottom. So a shortcut is to hit the up arrow key. That brings you all the way down to the bottom. And there it is, option D, two-sample F-test. So run it. It's asking me, what am I working with, data or statistics? Well, I'm working with data. List 1 is in L1, so I need to change it on my calculator. Make sure it says L1. The second list, I put an L2, so I need to change it. Put an L2. Frequency is always 1. Remember, frequency, when we're doing these tests, tells the calculator that every time it sees a data point, how many times should it count it? Well, we want each data point counted once, so we're going to leave that as a 1. And jump down to alternative, and remember the alternative here just simply has to match my alternative. My alternative is greater than, so I'm selecting greater than. And then calculate or draw. So if I calculate, it's giving my p-value 0.0796. So before I go any further, I want to do one more thing. I want to go back to that F-test, and I want to run it again, just so you can see it in case you haven't tried this yet. I'm going to select draw. When I select draw, well, actually, when I selected draw, there's a bunch of junk on there. I'm going to fix that real quick. If this happens to you, and guarantee you it will, what that's saying, I got a bunch of stuff active here. I'm going to turn my stat plots off. Oops. Turn those off. And also, I'm going to hit my y equals key and look for equations that may be in here. I did a normal plot, and I know, there it is. I know x is in there because that's what the normal plot uses. That's that line that you see in the normal plot. So now I should have everything cleared off. I'm going to run this test again, and I'm going to tell it to draw. That's better. And the point I want you to see here is, what shape is that? That's the F curve, and it's skewed right. And what it did is it shaded in the area. There's your p-value, 0.0796. And the F statistic, that ratio of those two sample variances, That's what the F statistics actually given you, is 2.17. So, back to the computer screen here. The p-value was, see, 0.0796. This is greater than alpha. Therefore, that brings me to my decision of fail to reject. The conclusion, based on this data, there is not enough evidence to suggest the new technique or process, whatever you want to call it, reduces the variability and let's say the number of blemishes. Okay? So, we do not have sufficient evidence. Our p-value is too big, based on an alpha of 0.05. If we're using L5, 0796 is definitely bigger. So we would fail to reject and say, based on this data, there's just not enough evidence to suggest it really does reduce variability. The difference that we saw, because if you take a look at the sample statistics, you will see that the standard deviation is going to be smaller for the new process than the old, but that could just be by chance. There's not strong enough evidence to say, hey, it really works. Not at this level. If you use alpha of 0.10, meaning you're saying you're accepting about a 10% chance that you're going to do the wrong thing, you're going to commit a type 1 error, then you would reject. Bottom line is, when I look at this, I'm thinking of this as my calculated probability of committing a type 1 error. So if I were to reject and say, I think this new process really does reduce variability, almost 8% chance that I did the wrong thing. I'm wrong. That I'm going to be wrong. Okay, that's it for the idea of the F test. Next, let's take a look at a similar situation and get at the answer or get at the question of, does this new process actually reduce the number of blemishes? Maybe if the variability is the same, but it will reduce the number of blemishes, that's still a good thing. If we can reduce the number of blemishes without increasing the variability, then maybe this new process is still a good thing to go to. All right, let's take a look at that now.